The broken promise of quarks, our promise, our children's future. Physicists like to break things into their smallest parts to see how they're made. When things get smaller than 10 to the minus 15 meters, there's not much space to get complicated. The physics of the very small should simplify. When Murray Gell-Mann introduced quarks in 1964, there were no personal computers, and the mainframe computers had only 64 kilobytes of memory. Quarks promised to provide the underpinnings of the natural world, but in the last 50 years, no one's isolated a quark. The promise that quarks offered was long ago broken as quark theory gained color and complications rather than simplifications expected for the smallest things in the universe. Fundamental questions were ignored and transformational ideas left unfunded in favor of bigger machines to test quark theories. We can't wait anymore for progress. Quarks are now slipping into elementary and high school classes to teach students the fundamental laws of the universe. We hate to lie to our children. What quarks don't explain is far greater than what they tried to illuminate. Children are asking fundamental questions that are not addressed. They ask questions that we must answer. What are charges and masses, and how are they formed? What are protons, neutrons, and electrons? Protons weigh much more than electrons. Doesn't that mean they're bigger? What causes the strong force? Does light have gravity? All their questions can be reliably answered now, but not by quark theory. It's embarrassing. All other fields have made exceptional progress as we adapted in the communication age. Physics has not. Much of the funding has gone into fringe physics to support large facilities and big science. Is size really the most important thing? Setting up a death match between big science and the rest is not the way to go. Nuclear fusion reactors have been explored for over 60 years. It's been challenging to get more energy out than was used in the process. Current ITER fusion design is far over budget and unlikely to produce a reactor in less than 30 years from now. The 20-year plan is for much more. ITER is just the beginning. But where's the advancement to fundamental understanding? Where's the bang for the buck? Much of physics funding has gone into quark physics. A great number of physics graduate students are lured into nuclear physics, only to find that jobs in nuclear physics are few and far between. For junior scientists, the playing field is very difficult for everybody. And quarks can't answer the fundamental questions. Quarks don't exist. Experimental data identified 3 kinds of scattering off a nucleon. True, but the interpretation of nucleon internal quarks turns out to be wrong. The scattering patterns were impacted by 3 kinds of electromagnetic field structures within a nucleon, north and south magnetic poles separated by transverse electric fields. It's no more possible to separate quarks than it would be to cut a current-carrying loop in order to try to separate its north and south magnetic poles. Quarks are not a productive path. Generations of physicists have found jobs in industry or evaluating grants for national agencies or evaluating research papers for publication or teaching. Unfortunately, they don't recognize any theory but quarks as the basis of the natural world. We have trained our scientists to reject inquiry in order to show loyalty to the nuclear consortium they joined so that their names would be authors on research papers to which they didn't contribute. At last count, each Jefferson Laboratory publication had 657 author names on it. Few of these authors participated in the work, but all got the credit. This is madness. Worse, the effects filter into other fields. Chemical physics, astronomy, and education are not willing to accept work that competes with quarks. It's clear nuclear engineering has been held back. Since nuclear processes and the strong nuclear force are poorly understood, transformation of nuclear energy into usable electricity still loses 70% of the energy using 18th century steam turbine concepts of heat capture. Only a few may even participate in physics inquiry and publish results. Certainly no one could complain and still be considered for funding or publication. Who loses? Our children. Without funding, we've worked diligently to answer their questions. But how can children believe the answers if texts say something totally different? We have answers to their questions on natural phenomena, even on the small scale. Start with protons and electrons as charges. They're robust, self-generating potential structures that last as long as the universe will exist. As such, they're electromagnetic and are shown to have magnetic dipole moments. Electromagnetic fields and forces become phenomenally strong as distances get tiny. Gamma rays are extremely short waves, each carrying a tremendous amount of energy. Electromagnetic waves are robust potential structures with longitudinal geometry. Photons are modeled along a cylinder with propagation along a ray. All robust structures are generated from periodic oscillations of electric and magnetic fields. Circularly polarized photon fields are invisible. Represent their compact structures using slinkies to help envision the field geometry and magnets to represent chargelets. Each chargelet is a swirl of potential, a spiral vortex, a current loop. These maintain a strong dipole magnetic field along a chain of chargelets. The silver magnets are positive, the black magnets are negative. These robust chains orbit around the cylinder center while moving along the cylinder at light speed. The revolution of change causes electric and magnetic fields that are periodic in time. Electric fields cause pushing or pulling. Magnetic fields produce two-dimensional circulation, isolating the structure in 2 dimensions so the photon moves only along a one-dimensional ray. This photon encounters a proton. A proton looks like a photon that's chasing its tail. The positive chain dashes around a toroidal loop and revolves through the donut center. All of the individual chargelets cycle through the many poloidal loops of a slinky toroid. The inner magnetic field is multiplied by the number of looping chargelets. The strongest magnetic fields are maintained near the center of the toroid shape, around the inside of the donut. These provide the huge magnetic energy responsible for huge proton rest mass. If a photon collides with a proton, strong proton electric fields repel the positive photon chain long before the two objects could touch. The negative photon chain is stripped off the photon by the attractive proton target. The ends of each photon chain join. We see a retreating proton with strong inertia and a trailing loop of negative charge that embeds itself across the target side of the newly formed proton. Strong internal magnetic fields exclude the negative chain from the interior of the proton toroid. A neutron has been formed. Let's call the neutron negative chain a negatron because its shape's influenced by the internal proton. It's different from an electron. Both the proton and negatron revolve around the toroid axis. If the neutron chains are disrupted, the two chains retain their individual magnetic moment and energy, but separate. The negatron adjusts its shape slightly to fly off as a lightweight electron. With this visualization, let's answer the questions posed by our children. What are charges and masses? A charge is a robust, localized, self-generating potential structure with internal currents. A mass is the inertia caused by the localization of the potential structure. It's difficult for a rotating gyroscope to fall over. It's difficult for a photon ray to turn sideways because it preserves local magnetic dipole moment around the sides of the structure in 2 dimensions. It has inertia. A proton has 3-dimensional inertia, so it's difficult to change its rotation or to move it. Charge and mass both result from robust photon structure reflecting and circulating into compact self-generating structure. Where do charge and mass come from? On our scale, mass is conserved, yet astronomers show that on astronomical scales, mass continues to increase. This suggests that mass creation is difficult and uncommon. Astronomers say that the universe holds much more energy in electromagnetic waves than in all the masses in the universe. One way of forming masses is pair production by 2 identically high-energy photons hitting dead on. That's very unlikely to happen. What are protons, neutrons, and electrons? A proton can be generated and modeled well by a photon chain that collides, resonates, localizes, and revolves about a toroid. Poloidal currents through a donut support toroidal internal magnetic field around the donut. A neutron is generated with a proton inside, providing guiding internal fields to orient an outer negatron loop. Perturb a free neutron, and the outer negative field structure escapes, forming an electron as beta decay. In collisions, if a robust geometry results, then robust potential structures persist. Maxwell's equations of electromagnetism preserve magnetic and electric energy in spiral, toroid, and dipole geometries, but not in spherical field geometry. Only protons, neutrons, and electrons are robust elementary particles. Many nuclear scattering experiments create transient field structures that last only 10 to the minus 21 seconds. If the resulting geometry is not robust after a collision, then the structure devolves, providing dying vacuum fluctuations throughout the potential background. Space is not empty, it's full of oscillating potential. Note that the neutron decay process is chaotic. Energy distribution is sensitively dependent on the geometry of its initial binding and spin. A massless neutrino is not a necessary product of beta decay. Protons weigh much more than electrons. Doesn't that mean that they're bigger? A proton's poloidal internal currents maintain strong toroidal magnetic field multiplied by the number of poloidal loops. The huge energy of this robust internal field explains the rest energy and mass of a proton, 1,836 times the mass of an electron. The negatron had no complete poloidal loops and no internal toroidal magnetic field storage. Only a weak magnetic field was maintained, providing little mass to slow a flexible escaping electron. Similar geometry guides gyration bounce drift electron motion about the Earth's magnetic field in the magnetosphere. Electrons are bigger than protons and slightly larger than a neutron. The proton just has more mass. More mass is commonly more compact, as is the case for a black hole. It has gravity, but is confined to an itty-bitty space. What causes the strong force? Both protons and neutrons act as extraordinarily strong magnets at nuclear scales. Magnetism dominates if nucleons are very close, a few times 10 to the minus 15 meters. The strong force is magnetism. Nucleons are not spherical and don't have spherical electric fields that repel in all directions. Nucleons are magnets that align and bind along mutual magnetic field lines. At the poles, transverse electric fields are reduced. To get close enough to bind, nucleons must be moving very fast. Binding happens only in the dense high-temperature core of a star. There, the ends of chains of nuclei join to form loops, and loops are crushed into lumps, that is, nuclei of the elements. No factory on Earth could manufacture one element from another. In gravitational lensing, how can gravity bend light? Gravity needs masses to work. Does light have gravity too? Gravity is a weak, distant attraction. Light has two-dimensional inertia. It's difficult to bend it. It has characteristics like electrical attraction. In fact, on all scales, neutral objects have oscillating external shielding by negative charge. Over astronomical distances, weak electrical interaction occurs between electromagnetic emissions from an astronomical object and rays of passing electromagnetic waves. The grand unified theory, GUTS, is electromagnetic on all energy scales. Quarks have broken their promise, obscured clarity, and lied to our children. Our children don't appreciate quarks, the emperor's new clothes. Help us to restore inquiry to physics in America.